everyone, so in this video we're going to do more on absolute value functions and their transformations. Okay, so I do have a worksheet on Google Classroom that goes along with this video, and then I also have a practice worksheet for you guys to try some questions on your own. Okay, so in number one we want to graph y equals the absolute value of 1/2 x. And our interval is going to go from -6 to 6. All right, and you'll notice in the table I only filled out even values for the domain. Okay, so I'm going to clear what I have in my calculator. All right, in y1 we're going to type in the absolute value of 1/2 x. So I go to math, scroll over to number, choice number 1. So alpha y equals (1/2 x). All right, so I'm going to do second graph. And you'll notice the reason why I only chose the even values for the domain was to avoid graphing fractions. Okay, so we got -6 is going to be 3, -4 is 2, -2 is 1, 0 is 0, 2 is 1, 4 is 2, and 6 is 3. Okay, so I'm going to copy those values onto my table. And then we're going to graph them. Okay, so again, the absolute value graph takes on that V shape, and I'm not including arrows because they gave us a specified interval to graph. Okay, so that's what our graph should look like. All right, so our domain was given to us, right? Our domain went from -6 to 6. And then our range, the minimum y value in the table and on the graph, is 0. So my range is going to be all y values greater than or equal to 0. And in this case, because we're only graphing that specified domain, all y values that are also less than or equal to 3. Okay, so my range goes from 0 to 3. All right, so now they want us to compare this graph to our parent graph, right? Our basic y equals the absolute value of x graph. So I'm going to go back to my calculator. In y1, I'm going to clear what I have, and I'm just going to type in the absolute value of x. Then in y2, I'm going to type in the absolute value of 1/2 x. Okay, so when I hit graph, there's y equals the absolute value of x. And in red, this is y equals the absolute value of 1/2 x. So you'll notice here the vertex stays the same, right? My vertex is still the origin 0, 0, but now the points move further away from the y-axis. All right, so this is something that we call a vertical compression. So when we compare these graphs, we're going to say that the points move further away from the y-axis. All right, and again, the name given for this transformation is a vertical compression. All right, let's look at the next one. So the next one, I didn't require you guys to graph it. This was something we can just do on the calculator. So it says graph f of x equals the absolute value of x, and g of x equals 2 times the absolute value of x on your calculator. How do these graphs compare? Okay, so we're going to go back to y1. So that's absolute value of x. So now in y2, we're going to do 2 times the absolute value of x. Okay, so in y1, we got f of x, which is the absolute value of x. In y2, we have 2 times the absolute value of x, which is g of x. So I'm going to hit graph. Okay, so again, you'll notice that the two graphs have the same vertex, which is the origin, but now my points are getting closer to the y-axis. It's almost like the graph is getting skinnier, okay? So this is what we call a vertical stretch. All right, so when we describe how the graphs compare, we're going to say the points move closer to the y-axis. And this is called a vertical stretch. Okay, last one to go over, we're going to graph y equals the absolute value of x and y equals -1 times the absolute value of x. Okay, so make sure you're using the negative button in your calculator. Okay, so there's my two equations. So in blue is the absolute value of x. In red is the negative absolute value of x. So you'll notice that basically my graph flipped over the x-axis. All right, so when you stick a negative in front of the equation, you get a reflection over the x-axis. Okay, so here we're going to say y equals negative times the absolute value of x is the graph y equals the absolute value of x. Reflected over the x-axis. Okay, so now what we're going to do is we're going to summarize all the rules that we've gone over. And again, these rules don't just apply to absolute value, they apply to all functions. Okay? So when I take an equation and I add a number at the end, that's when you're going to shift up C units. Okay, when I subtract a number at the end, then we're going to shift down C units. If we add a number inside the function's argument, so that would be like inside the absolute value bars, we're going to shift left C units. Subtracting a number inside the function's argument is going to shift right C units. Okay, so those 4 transformations are the ones we've already gone over. All right, when we multiply by a negative, that's when we reflect over the x-axis. Okay, when we multiply by a number greater than 1, that's a vertical stretch. Okay, so that's when the points are closer to the y-axis. All right, that's when your graph gets skinnier or narrower. All right, when you multiply by a value that's greater than 0 but less than 1, that's considered a vertical compression. So that's when the points move further away from the y-axis. Okay, so now we're going to take a look at a few examples. Okay, so this first one says write an absolute value function with a vertical stretch of 5 units and shifted to the left 8 units from the parent graph. Okay, so since they're asking for a function, we're going to use function notation. So we're going to start with f of x. Vertical stretch of 5. So that means we're multiplying by 5. So we're going to stick 5 in front. And then shifting left 8 units means we're going to add 8 inside of the function's argument. So that's what my equation would look like. Okay, number 5 wants you to describe or state the transformations that occurred. So there's 2 transformations that occurred here. When I subtract the 9 at the end of the equation, that means we shift down 9 units. And then the negative in front means we reflect over the x-axis. Okay, number 6 is the same thing, state the transformations. So when I subtract 10 inside of the absolute value symbols, that means we're going to shift to the right 10 units. And then the 1/2 in front is a vertical compression of 1/2. Okay, so then I also have a handout up on Google Classroom. All right, I'm going to go through the odds and then the evens you guys can try on your own. All right, so number 1 says, what will be the equation of the resulting graph if the graph y equals the absolute value of x is reflected in the x-axis? Okay, so to reflect in the x-axis, we just multiply by a negative. So that's going to be choice B. All right, number 3. When compared to the graph y equals the absolute value of x, the graph y equals the absolute value of x minus 8, well, when I subtract 8 at the end of the equation, that's when we shift down 8 units. So that's going to be choice C. All right, number 5. When we compare these graphs, what happens? Well, I'm adding 5 inside the function's argument, inside of the absolute value symbols. So that's going to be shifting to the left 5 units. So that's choice C. And then 7, write an equation for the function y equals the absolute value of x after a shift of 7 units to the right. Okay, so if I want to shift left or right, I have to be inside the function's argument. And if we want to shift 7 units to the right, we're going to subtract 7. All right, so I hope this was helpful. If you guys have any questions, you can always send us a comment on Google Classroom or email us. And then there will be a Google form for you guys to complete by Friday.